Three, two, one. Welcome, one and all, to Math 2070 Online Applications of Linear Systems. Let's go. Alright, so we're going to look at two particular applications coming from the real world. And the first, one of my favorites, the balancing of chemical equations. So suppose I have this chemical equation here, and I want to balance it with the assumption that the coefficient on the H2S is 3. All right. Now, if you're a chemistry person, you probably have a way of solving this. I have not done chemistry since 11th grade, where my teacher was a guy named Mr. Silver, so obviously, with a name like that, you're the only career you could have. Anyway, so you may have a way of solving this that doesn't use systems of linear equations or any linear algebra, but I've got a way of doing it, so we're going to check that out. So here's our first problem we'll look at. We're going to look at another one in a little bit, but let's break down how we're going to do this. So the chemical equation, I can rewrite it as follows, where I have these sort of unknown coefficients out in front of my chemical elements. So I've got my iron, sulfur, hydrogen, chloride. Correct, right? If I'm wrong, leave a comment. I won't read it. Chloride, chlorine. What am I talking about? I don't know. Anyway, chloride. That's a real chemical, right? Ugh. Anyway. So, note there's 4 chemical elements here, whatever those symbols mean. I knew Fe was iron. Come on, give me some credit on that one. Now, the compounds can be written as vectors as follows. So here I've got 2 iron, 3 sulfur. So iron, we're going to have that represent the first row. So wherever we see an iron show up, that will be represented as such. There's 2 of them here in my first one, so I'll have a 2. There's only 1 there, so we'll have a 1 up there. Sulfur, we'll have that correspond to the second row. Here we have 3 of them. We have none, we've got none, we've got 1. The third one will have hydrogen correspond to that. No hydrogen, 1, none, and 2. And then the cloatium here, we will have that represent row 4 here. And here we see that there's 1 that shows up there and 3 that shows up here. Okay, so that means then that this up here is really this vector equation, x1 times our first vector, x2 times our second, x3 times our third, x4 times our fourth, and they're equal as follows. So note that I can subtract these over here, and it will convert over to a beautiful homogeneous system, and in particular as an augmented matrix, it can be written as follows. Get it in ref form, and then this gives me a system. And now note, we have a consistent system. The rightmost column is not a pivot column. Note I have 3 pivot columns. But I have 4 variables, but 3 pivot columns, so that means that I actually technically have an infinite number of solutions. But if we let our mind float back, we were given some extra information. We were told to balance it when the coefficient on 2 hydrogen sulfur was 3. So plugging in x4 equals 3 gives me then x1 is 1, x2 is 6, and x3 is 2, thus giving me the beautiful balanced equation, as you see in front of you. And like I said, if you are more of a chemistry person, you might have other ways of solving this, but here you see that we have a nice robust method using systems of linear equations. Good stuff. Alright, now let's look at another wonderful application. So our second problem for this video is as follows. Let's say I gave you a network system shown as follows. I have 3 nodes, A, B, and C. A has an outflow and 2 inflows, 1 coming from B, 1 coming from C. C has an inflow and then 2 outflows going to A and B. B has 1 outflow going to A and an outflow just going out, and it has 1 inflow coming in from C. Now, suppose that we want to do the following. So, the general flow pattern has been given to us, as we've verbally described. We can visually see it here. Now, assuming that all the flows are non-negative, what's the largest possible value of x3? Now, what we're going to assume here is that inflow and outflow need to be equal. So, in other words, at the node A, x1 and x3 together need to match the outflow, which is 10. So I must have x1 plus x3 is equal to 10. Likewise, the inflow on C needs to match its outflow, so x1 plus x2 needs to be 20. And then on B, its outflows, x3 plus x4, need to match its inflow, x2. And there are those equations in each intersection. So again, we're under the operation assumption that the inflow and outflow need to be equal to each other. Alright, so that gives me, hey, 3 equations to work with. And I can rewrite it as an augmented matrix, which I can then ref. I'm sorry if that was a little bit too quick, but anyway. Note here, x1, x2 is equal to 10. Here we have x2 minus x3 minus x4 equaling 0. And here we have x1 plus x2 is 20. So I can ref this now, giving me this. Note I have 3 pivot columns, 1 here, 1 here, 1 there. However, there are 4 unknowns, so we know we all have a free variable. In particular, x3 is a free variable. And the question we were given was, I want the flows to all be negative. What's the largest x3 value you can pick to keep things non-negative? Well, x3 here can't exceed 10, otherwise it will go negative. Beautiful. Alright, and there we go. 2 fun little applications of systems of linear equations. Good stuff. Alright, so we took a little pause here in our study of systems to check out a couple little fun applications. Next time we'll dig a little deeper into some more theoretical things about them. So I'll see you in that video.